Okay. Can you hear me? That's fine. I'm really happy. So I hope you enjoyed the conference. I hope you enjoyed the lunch. And yeah, that you won't fall asleep. But let's see how it will go. And I'm Maciek. And in previous times where I've been on this conference, I'm here like third or fourth time, I usually display stuff like that, right? So I've been working at TOE, creating our load code tool Newsnacker, and I've been working in Java and the Scala, mostly functional programming. And I did it for like 17, 18 years. Well, maybe not the Newsnacker, right? But I've been at TOE for 14 years. But as you can see, I'm getting old. And most of the speakers here are also getting old. You can see by, for example, Grzesiek. And what happens is that there's this, Jarek is not here, so I have to talk about you. So there's this thing called middle age crisis, right? And some of the folks are changing wives for younger, cars for faster, but I love my wife and I hate cars. So what did I do? I changed company for a younger one. So my current company is turning 6, I think, in 2 weeks. And faster languages, right? We'll get to that. So currently I'm working at Hyperexponential. We're kind of like insurtech company, but we are kind of like more ethical than the ones that sell your medical data to the company, so that's fine. And I'm working with quite different technological stack, mostly with Rust and with Python. We also have quite a lot of code base in Kotlin and Go, but I won't be talking about that because Kotlin is known to probably all of you, and Go is kind of like abomination, so we'll hide that. Right, so when I changed company to Hyperexponential, what I wanted was change, right? And I was kind of like expecting that the change will be kind of like drastic. How drastic? Let's look what may happen. We may want to use GNU indentation style, almond indentation style, sorry, or some other indentation styles. Go to Wikipedia page and you can see that there are at least 6 different programming styles. But fortunately, in most of the languages, what one was kind of like this one. So we're kind of like happy with that. I didn't have to bother with all the other indentation styles, which kind of like made me happy. But still, the differences can be quite interesting, right? I'll be showing a bit of Scala code, but don't get too scared, right? It shouldn't be that more different to the Java one. So you can see that the most visible differences is, of course, here we have JVM snake case, and here we have camel case, and here we have snake case. But also there are kind of like also interesting cultural differences. For example, in JVM world, it's natural for us to write the types, even if they can be inferred here on the left. And here I learned that in the Rust, or at least some part of the Rust community, we have good type inference. Please don't write types here, just write it over there, and type inference will take care of itself. So these were kind of like small challenges, small surprises. But on the other hand, there's a lot of things that are kind of like surprisingly the same. So this is a question for you. Do you know which languages are those? Yeah? And? Okay. We don't have too much time, so I'll answer this question. So this is Python and this is Scala. Can you see 10 differences? No, you can't, because there are no 10 differences, right? So the only difference here is this semicolon and this arrow, right? But over the years, the syntax of Python and Scala grew quite similar, right? This is Scala free code. Yeah, I know I forgot the parentheses, but bear with me with that. So here we have optional braces, and here we have kind of like, I would say, proper generics, right? This is fairly new Python code, but still, you know what I mean, right? And also in Rust, I have traits. In Scala, I also have traits. And if I had placed for some code in Java, I would write interface, and you can see they are kind of like similar. Okay, there's FM, there's dev, but you know. And also there are other similarities that appeared only recently, right? In Scala, we always could do proper pattern matching. In Rust, we so can do proper pattern matching for a long time. And in Python, we can do it from, I don't know, I think around 3 years, right? Again, if I had a Java code, I would also be able to put some nice pattern matching structural ones for the records, case classes, or whatever we call it. And still, there are some small annoying differences. This is the one that I can't put up with after 8 months writing Rust, and I still write it the Scala way: X match versus match X, or the other way around. Oh my God! I think I wrote it badly on the slide, but yeah, let's see. Anyway, in the last, I think, 5 to 6 years, the syntax became pretty similar. Of course, it's different, right? But if you compare the Python code from like 6, 7 years ago and the Scala code, they would be vastly different, or the Java one, right? But right now, it's kind of like there are more and more features that are, well, appearing in both of the languages. And for a side note, I know probably most of you hate Scala, but still, I would like to say that in JVM, Scala was a pioneer. Right now, okay, Java caught up, there's Kotlin, but still, I think some credit, we should give credit where credit is due. So at some point I started thinking, maybe it's like, this is a famous quote for Gattopardo by Giovanni Tommaso di Lampedusa. So yeah, you can read the book, it's really great. At some point I started thinking, okay, so maybe everything must change. This is me, my company, the stack, and so on, so that everything remains the same. Well, if that was the case, I wouldn't be here talking to you for like yet another 40 minutes. So let's see some of the more kind of like subtle differences. We'll go beyond the syntax to see how seemingly same concepts can result in different behaviors, different idioms, because of the way they are implemented, because of the way how the language works underneath. So let's see I would say the basic data type, right? This is the string in Python. I'll write this type annotation. This is the one in Scala. Okay, of course in Java it would be kind of like very similar. And this is in Rust, right? There's kind of like peculiarity because we have kind of like 2 different types of strings. We won't get into that, but one is kind of like more similar in name to Python, one is to Java. Here's the literal, I'm creating that. But so far so good. They seem quite similar. But then interesting things happen. What happens when I want to do something with the string, right? So in Python I have nice string interpolation, I have some methods on strings. In Scala, the same, right? You can also do, and in Java it would also be the same. Whereas in Rust, it's a bit different. It's a bit different because I have those methods like push string, make ASCII. Let's leave it for for some time. I have those methods, but if you have a look at those, you can see they don't return anything, contrary to what Python and Scala version does. And this is the first interesting thing that you can pop into your mind, that this string type in Rust is mutable, right? So when I do push string, well, it changes the behavior of this title variable. Whereas both in Python and in Scala and in Java, of course, right, as you all know, the strings are immutable. So this is different. And the same when we go to kind of like data structures like the list, right? In Python, in Scala, it's kind of like natural. It was, for me, very natural for many, many years to use immutable lists and other persistent data structures. In Rust, it's different, right? The list is called vector. Let's not care too much about that. But this is mutable. So it's, again, more similar to Python. Of course, in Java and Scala, we have mutable lists. So this is not so different. But in Scala, this is kind of like more idiomatic code, right? That there's immutable data type, persistent, and then you just create new ones if you want to append or do something with that. Of course, we can also have different methods of creating new lists, of operating on that. And in Python, we have for comprehension. In Scala, we have for comprehension. If you format it the right way, this is maybe not the most Pythonic code one can see, but you can see they are kind of like fairly similar. Of course, here the yield is at the top, here is at the bottom, which is kind of like mind-blowing how Python folks can do it. And in Rust, you do something like this. Again, you can have some, I would say, you can have some closure or lambdas that you apply to the list. But here, if you look at this is more like in Java, right? As if I have stream, and here I collect, and here I explicitly say, okay, I need to create this new vector. Again, this is because all the memory allocations in Rust should be kind of like explicit, right? Here I'm creating a new list. It's under the hood. I cannot see it. Here I'm also creating new lists, and that is because of the braces, right? But here, creation of the new object is pretty explicit, right? So when I went to Rust, I had to learn to be much more mutable than I got used to. And it also meant that some of my algorithms had to be different, right? For 20 years, my default algorithm I would use to traverse anything was recursion, right? And here I have to learn in my current company that no, recursion is kind of like, it's possible, but it's not idiomatic. I should go with the stack plus loop solution, right? So I can model some simple tree. In Scala, I would just use, recursive code to compute, I don't know, some of the values in the nodes. And here in Rust, this idiomatic solution, at least as I've been told, is more like, okay, I have to create the stack manually, it's mutable, I collect the result, again, in mutable variable, and here I iterate over it, and so on. So, of course, both the solutions work. This is still quite not so natural for me, right? But on the other hand, I accept the fact that in some way it can be much more effective, right? Because if you look at the Scala code, there's no tail call optimization here. This code is not tail recursive. In Rust, again, there's no tail call optimization. So I can understand that this is maybe more close to the bare metal. But still, this is something that I find kind of like weird, right? Because for so many years in Scala and functional programming, I've been learning that, okay, mutability is bad, right? And of course, the folks in Rust have their own ways, right? They don't want to have automatic garbage collection. They have to maintain some predictable order of allocations and stuff like that. And if you don't like it, well, choose different language, right? And in some cases, I feel we should also do the same. But still, there are valid cases when we want to be able to control the allocations to be closer to the bare metal. But still, this bad mutability kind of like is not something we would want to have. But thinking about mutability, you can find this old quote, I think, from Martin Odersky. That is the creator of the Scala, and saying that shared mutability is the root of all evil. And this is certainly true, but in Scala and functional programming, we've been focusing on the mutability, right? If we are immutable, we can share freely. Whereas in Rust, it's kind of like the other way around. We will control sharing so that we can be mutable. This is kind of like interesting twist, which takes kind of like a lot of time to adjust, right? So in Rust, what would happen is that we may have arguments to the function of few different types. One is saying, okay, if you pass this argument, it means you are transferring the ownership of a certain variable or structure or something like that to this function. Here, I'm saying, okay, I'm borrowing the value, so the caller of the function still owns this value, but I can mutate it. And here, I'm just borrowing it for reading. I cannot mutate it. I can only, this is kind of like shared shared board, so it calls. So there are certain ownership rules. One piece of data, one variable can have only one owner. You need to have exclusive borrow. At one time, you can borrow, I think, only once to mutate it, and the shared borrows for read, and some of the operations require this exclusive ownership. We won't get into the details because that would take a lot of time, but still there are certain rules, there's certain syntax that has to be observed, right? And then, for example, I have a function that requires this ownership. It means that here, if I create the variable, if I invoke this function, I can no longer use this variable. This line would cause compile time error. Whereas, if I only borrow it, this is a borrow, right? I'm borrowing the variable. Here at the end of this function, the borrow is returned, so I can invoke something on the list. At the beginning, it seems simple. Of course, if you go deep into that, it's mayhem, and it's kind of like sometimes it's really difficult to get things work. Fortunately for JVM developers, there's magical method called clone, which means that we're effectively cloning all the data. We have this allocation. This is not idiomatic code, but at least you can progress, right? In Java, we also have clone, right? But you don't normally use it, right? Because you can pass whatever data you want to whatever function you want, and it's kind of like still working. But here, this is kind of like a magic trick that can save you at least a bit of trouble, I would say, right? So this is the interesting part, that in Rust, the mutability and the ownership can be thought of as kind of like an effect modeled in the type system. This took me quite a while to understand that I can think about it this way. And this, again, brought me a bit closer to the world that I know, that is the kind of like Scala one. Because in Scala, if you use certain, I would say, programming style, if you use certain libraries, again, you can model certain outside effects in the type system. Like here, we are saying that this function does some I/O operation, this one too, and here, yeah. And okay, I won't get into all the monad talk because, yeah, we're in Java conference, but still the idea is kind of like the same, right? So it helps to digest this concept of the ownership. And again, there are some interesting hack you can do in Scala. Usually at some point you think run unsafe async, and Rust is kind of like similar. If you want to say to the compiler, okay, please compiler, I know what I'm doing. I know you're thinking that the rules of the game are not satisfied by me, but I know what I'm doing. I can also make unsafe, and it will break or not. Yeah, but this is somewhat similar if you think about it in this way, and also similar to stuff that can happen with functional Scala code. You end up with something like this, and that is totally unreadable function signatures. Again, we won't be going into that, but you have to be prepared that some things will exist. And you also can cheat a little bit and say that, okay, this is my variable. I'm pretending that it's mutable, but in fact, somewhere inside, there will be some modifications. So this is well and good, but you may start to wonder, does it really help? Well, again, in some way it helps, right? Because you can control all the allocations, you can run it without garbage collector and so on. But there are also a few kind of like, I would say, not obvious benefits of this explicit ownership rules. And one of them is connected to the allocation of external resources. So this is the code that we would write in Java. I don't remember, like Java 5 or Java 6, right? Long, difficult, catching exceptions and so on. But now we'll be doing something like this. Nice try with resources. And in Scala, there's also using construct, right? So still it's quite fine, right? We are allocating the resource, and at the end, some method will just release it. In Python, it's kind of like similar, right? You can use something like this with try finally, but most of the folks would be using the context managers, which look quite similar to try with resources. And here, of course, the Python folks wouldn't care if the close method crashes or not, because they're not into the business of handling exceptions properly. Yeah, and in Rust, what we would do is something like this. Again, you kind of like have the path, which is kind of like similar to file. You're calling open. You're reading file to the string, which is again mutable. So it seems, well, yeah, we have to put up with that. And that's all. So the question is, did we forget to close the file? No, we didn't. It just works like this. And this is even more apparent for when you're interacting in Rust with logs, right? This is the mutex one. And this is under the hood using the pthread library, I think that Jarek told about. But anyways, so here you have mutex. You are calling log. You can assign some value that's guarded by the mutex. But again, when you are actually releasing the mutex, you don't. It's done automatically. And this is called by the pattern, which is also known from C++, if any of you are into that. That's called resource acquisition is initialization. So because in Rust we have kind of like explicit ownership rules, we know where the one and only owner goes out of the scope. So this variable that represents the open file, our resource, is no longer needed. And then we can invoke the drop method, right? Which would close the file, which would release the mutex, and so on and so forth. So, in fact, somewhere here, the file will be closed just when it is no longer needed, right? So, there are a few ways where we can kind of like force releasing or closing the file. We can explicitly say drop. And then, if I do something like this, I explicitly drop this file variable, the file is closed, and here again I'll get a compile time error, right? Because I already, dropped the ownership of this variable. Also, interesting pattern that is very often used is that I do those file operations in separate block, right? So here, the file is kind of like a local variable. I interact with it, do something, read it. But at the end of the block, this file variable is no longer used. So it can be dropped and the file can be closed. But this is because I know that I cannot, at this point, this file cannot be used by any of the data structure here because of the clear ownership rules. Like so here I can do something like this to force closing of this file here, and I can start different operation on the same file. So this is kind of like in contrast with JVM, right? In JVM we have automatic garbage collection, and the finalize is kind of like not really used. It's deprecated. I know in more modern Javas there's kind of like replacements, but still closing resources in all the finalization methods are kind of like discouraged. This is not how Java should work, right? Because the garbage collector is kind of like automatic. We don't have control over that. And it will make our code, I would say, not predictable, right? Whereas in Rust, we don't have automatic garbage collection. We have kind of like automatic memory management, right? So the memory is deallocated kind of like also automatically, but there are precise rules, and we can know at which point in our code, the object will be dropped, and we can predictably invoke things like dropping. So this is one of the, I think, biggest difference between, our JVM world, also between the Scala and the world of Rust, and that is explicit ownership rules and the fact that we don't have garbage collector, we have automatic memory management. Sometimes it's very convenient, sometimes it's really pain in you don't know where, but it's certainly opens your mind to think about some problems differently. But I won't be talking about ownership more, because this is kind of like long and complex topic. So we'll move to a bit different topic, and let's look at this code, right? So again, this is Scala trait. We can think about it just like the Java interface, right? We have some methods, some can have default implementations, and at Rust, I can do something similar. Again, I have trait, it's named the same. I can have method, I can have method with default implementation. So far, so good. Yeah, and in Java, it will look the same. Seems reasonable. And again, in Scala, I can implement my trait. You can think implementing interface. I didn't code in proper Java for quite a long time, so I didn't dare to write the code with the records. But you can write it with modern Java and with the records. And in Rust, it's kind of like similar, right? You have class, you have structure, and you implement a trait for that. So far, so good. So at this point, you start thinking, okay, so is Rust object-oriented language? Because this is, well, you have interfaces, you have structures, you have methods. What's more? But the interesting point comes when you start to want to use this trait. And of course, you write this code like this, right? So I have a method and I have parameter, and it should implement this summarizable. And it won't work. Fortunately, Rust compiler messages are pretty self-explanatory and saying, okay, trait objects must include the din keyword. You still don't know how to do it, but when you add this din keyword, the code will compile. But this gets you thinking, why this is not the kind of like normal ideal case? Why do I have to put this special din keyword? And the answer is, this code is not deemed kind of like very idiomatic in many scenarios. I think if I put something like that in MR in my current code base, I would have to rewrite it. Let's say it like this. And the reason why is that we have to look at some implementation details, and that is the differences between static and dynamic dispatch, right? So I have some caller methods, and I want to call a method on some summarizable object. So the question is, how does the generated code in the runtime know that it should invoke the method from the news or the method from the book, from various implementations of the trait that implements the summary? And in different languages, it happens differently. First, let's look at the differences between the Python, which is kind of like the epitome of dynamic language, and Scala, which is kind of like, I would consider a static one, which is kind of like similar to what will happen in JVM, right? So the difference between the dynamic and static here is more about typing. And in Python, it could happen something like this. So I have the method, I have this object, I'm checking if there's a keys method. If there is a method, I invoke it. If not, I'm trying to see what the error was received, and then I can try to invoke different method. If there is one, it's fine, and so on and so forth. And this is, you could do something like this in Java, trying different methods and see if they could be found. But this certainly wouldn't be kind of like normal Java code, whereas in Python, this is kind of like standard behavior, very dynamic. You can encounter it, for example, in the standard library. Whereas in Scala, JVM, or in Rust with the din keyword, we have the object, right? This is our color of the function. And somewhere we have vtable, whatever it's called. In JVM, it's much more complex. But again, the runtime will look up for some pointer to objects where the definitions of the classes are stored during the runtime, and will choose the proper way of invoking the method. Whereas if the object that we want to invoke method on is the news or is book or wherever, right? So it's pretty simple. Of course, on the hood, it's much more complicated, but there is some indirection. We have to look up this pointer and so on and so forth. So in Rust, this is again deemed not very idiomatic, not inefficient. And the way how Rust should behave is that, okay, in this place of code, I know it's news, I'm invoking news method. This is book, I invoke news method. So far, so good, but how do we really want to achieve it? This is the difference, by the way, that we're moving from dynamic, such as Python, through JVM world, where the typing is static, but dispatch is dynamic, and then to Rust, where by default, the dispatch is totally static. So, if we want to have this dynamic dispatch, there's additional runtime cost, but with the dynamic dispatch, the code is smaller because at the point where it's run, during the compile time, we don't have to know which method to invoke. So in Rust, how would we actually proceed, right? I want to have signature like that, right? So I want to invoke some method on this summarizable object. So does it mean I'll just have to rewrite my code with 3 methods here for exactly one implementation? Well, fortunately, this is not really the case. We don't have to write all those methods for all implementations separately. And the solution to this problem are generics. Again, in Rust, they are generics, just like we have in Scala, and just like we have in Java. So you can see that, again, the syntax is kind of like similar, but a little bit different, right? Here we have square brackets, here we have those ones like in Java. But here, if we want to say that, okay, this generic parameter is summarizable, we have semicolon, and in Java we have kind of like more elaborate structure. By the way, if you think about it, how many times have you used this functionality? That you can, there's a method, it's generic in T, the T extends summarizable, and so on. Probably not that often as, for example, saying that, okay, I have array list with the type parameter T. And the reason is that in Java, we have the dynamic dispatch, so we can, in most cases, here it's sufficient just to write summarizable, and the code will work. But in Rust, the generics are kind of like the vehicle to actually not have to write the code for each and every trait implementation. So the way that it works during the compilation is that there's the monomorphization process, right? So when the method like this gets compiled, during the compilation time, we have to know what parameter T will be used. So whether we should invoke this method, or this one, or this, right? So we have one, in our code, we have still one method with generic parameter, but when the machine code gets generated, well, in some places, it will look like this, in some like this, and some like this. So we can think, so how will it go? At the beginning, I have one method that takes this generic parameter T. If I want to invoke this method, then again, I have this parameter T. It also has to be generic. And if I'm invoking and so on and so forth. So it's like, seems like turtles all the way up or down, and where does it stop? And in the end, what actually happens in the Rust code is something like this. Somewhere at the top, either at the beginning of the application or where we are parsing the data, there is this if or pattern matching. And here I'm using one concrete implementation of the trait. In this branch, I know it will be book. In this branch, I know it will be news. And then when the compiler generates the code here, it knows that, okay, here I have to generate code with the parameter T that is news, here book, and so on and so forth, right? So everything has to happen during the compilation time. And all those methods will be generated, so it means that the generated code will be a bit bigger, but still it will run kind of faster because we don't do this lookup in vtables of the dynamic dispatch. So this is the stuff that we want to remember, that Rust and generics are monomorphized, and they are kind of like a means to enable us sane static dispatch. Whereas in JVM, as you all know, the generics are subject to type erasure, and we have dynamic dispatch. So these are similar structures, similar language constructs, but they behave a bit differently, and they serve a bit different purposes. Which means that for generics that are subject to monomorphization, we can do interesting things like this. In Java, it would be difficult to write a method, an interface, sorry, that takes methods like this, like from default, and I'm returning self. From string, I'm returning self. Self meaning, well, here in this case, if I'm implementing the parsable for the book, that will be, I have to return book and so on, right? Because there's no type erasure, during the runtime, I know exactly, like here, this is one of the library invocations, here I know exactly which implementation will be used, and I can, well, I can invoke the correct method, right? Whereas in Java, we can't just have interface methods like that because there's kind of like nothing we can invoke it on. So this is kind of like also interesting construct that can be, that is possible mainly because of the static dispatch. And if you think about it a little bit more, and you are accustomed with Scala, again, you can understand that the similarity of the name, that in Scala I have trait, in Rust I have trait, this is very misleading because, in fact, what is the analog of the trait in Rust, in Scala it's called type class. Again, I won't go into the details. If you know Scala, you know what I mean. But still, it's kind of like very illuminating to think that the same method can mean, same name can mean a little bit different things. And if you start to think about Rust trait as a type classes, then everything starts to match, and you can understand why Scala compilation is so slow and why Scala bytecode is so large. Yeah, so there's one more interesting consequence of the static dispatch in Rust code, which is kind of like more closer to our JVM world. Because let's zoom out from the language and let's look at the way how projects are handling dependencies. Again, this is in all languages it's a bit similar right now. You can only see that the Gradle has kind of like weird syntax for dependency gauges, whereas Python and Rust have kind of like similar ones. But once we declare the dependencies, they are resolved. And the interesting thing happens is that in JVM, the diamond dependency help problem can arise. So our app depends on the one lib and the other one. And the first lib has a dependency of logging like SLF4J in version 1.1, and the second has a dependency of logging in version 1.2, right? And of course, 1.1 and 1.2 should be kind of like compatible, but if they are not, then we're kind of like in trouble, right? Because if we package all this stuff in one jar, it can't just happen that we have this implementation and this implementation, right? Yeah. Well, yeah, this is kind of like the diamond dependency hell. But in languages with static dispatch, like in Rust, we may avoid this problem because, again, when the code is generated, it's statically dispatched, and all the methods that that invoke values, for example, that invoke logging from this library 1, will have code generated that will know that it should invoke this version. And from library 2, they will know that they have to invoke this method, right? There's no dynamic dispatch, no problems in the class space, because there is no class space. Everything is static. So this will just work, right? Of course, unless the objects from those shared libraries will be passed through lib and our code, right? Because then, they will have to have the same version if they are to be used if they are to be transferred between the code in library 1 and library 2, right? But for the logging, the problem will just disappear, right? The lib1 will use logging in this version, and this lib will use logging in this version, yeah? Here? With the loop, it will be compile time rather, right? I think so. Yeah, yeah, definitely. But still, it's much better in this case, right? Which is kind of like similar. And if you think about it again, you can think about old unpopular technologies like OSGI. Probably most of you are not old enough and to remember what OSGI was, but this is kind of like similar problem that OSGI tried to solve. Well, unsuccessful. So Rust does it in, thanks to static dispatch, Rust does it in compile time, which is, yeah, I thought it was pretty neat and interesting. So the thing I want you to remember from this part of the talk is that in Rust we have specialization monolithization, and in Scala, or generally in JVM, we tend to write more generic code, and we have the dynamic dispatch and polymorphism. I don't have too much time, so time to wrap up. So the thing I like to end up with is that the syntax between the languages can get increasingly similar, but still various idioms and styles of programming are still remain the same, which can be quite misleading because when you see a code in one language, it can actually behave differently, perform differently. But in most of the cases, it's not a question of right or wrong. There's just different trade-offs, right? In Java, we want to write code kind of like faster. In Rust, they want to write code that works faster, usually because there are kind of like different problems with that. But of course, some of the things are just wrong, like the old Java did API or the Python decision that they don't want to support UTF by default in Python to both the errors took like ages to actually resolve, right? But in most cases, it's just like different trade-offs. And if you think about it, this is kind of like similar to the fact that we have different cultures. We can communicate in kind of like simplified English between, the Americans, Eastern Europeans, and all the other words, but still some of the interpretation of what we're saying can remain different, right? So there's this objective distribution. All Americans say that everything is awesome. We Eastern Europeans, by default, are saying that this is garbage and so on. And this is kind of like, there's no objective distribution, but just the British bias. But still, there are different cultures. And to get on, we have to respect the local rules, just as we move from one language to another, or from one culture to another, we should respect it. Local rules, local customs. And it's also quite interesting to be able to immerse in the community, right? So when I changed the jobs, I kind of like moved to a place that I would say actively hates JVM in some parts, right? So I have to learn everything from the scratch, but this was very interesting experience, and it allowed me to understand some of the things much better, right? So, yeah, this is the motto I would like to end up, and this is something that I kind of like had at some point of my hiring process, that we've hired you because you are open-minded, and this is something I also wish for all of us, so that we can be open-minded and we can embrace those different languages, customs, and learn from ourselves, each other, and so on. And I think that's all from me. Thank you. I hope you enjoyed the rest of the conference. And yeah.